The final part of our study of statistics involves what we call hypothesis testing. Now, the first thing I need to get across to you is what is a hypothesis, okay? And believe it or believe it not, this has actually made its way back into first year science, okay? It's a concept that the first years are quite okay with now, and they do understand exactly what it entails. But a hypothesis is a statement. That's exactly what it is. It's a statement, all right? Now, in science, the first years are told to pose a question, then they have to do a bit of research on that question, and then they have to come up with a statement that they want to experiment on, okay? So, for example, the average length of an earthworm in Ireland is, and they'll come up with, say, 12.5 centimetres, right? Then what they've got to do is they've got to experiment, they've got to get the results, they've got to come to conclusions, and then either accept or reject the original hypothesis. In mathematics, we do exactly the same thing. The experiments we do in maths are not the same, obviously, as the experiments that we do in science. They're mathematical experiments. But it's exactly the same thing in statistics. We come up with a statement, we then test that statement, and finally then, based on the evidence we have, we either retain the hypothesis or we reject the hypothesis. Now, the language is slightly different, okay? We either retain the statement that we made, or we reject the statement that we made. What we do not do is we do not say, oh, the original statement was correct, or we don't say, oh, the original statement was wrong. Those words are not used in hypothesis testing. In hypothesis testing, you make a statement, then you mathematically test it, and you either retain the statement or you reject the statement. Okay. That's just an introduction. So let's go through this and see exactly what it means. First of all, hypothesis testing, it's an extremely important part of statistics. Okay, it's a way by which, as we said in science, we can test a given statement, or maybe a precondition, or whatever it's going to be, something we state. Then we test it and see, do we retain that statement or do we reject that statement based on the evidence that we have. In statistics, a hypothesis is a claim or a statement about a population. Now, it's never a question, okay? Never a question. It is a claim or a statement, okay? So you could say, for example, 65% of people over the last 10 years have given up smoking. Now, there's a statement. So what do? That's a hypothesis. What do? We test it based on the experimental evidence that we have. In our case, based on samples, so therefore using statistics. Never the population is too big, but you're based on samples. A hypothesis test is a procedure for testing a claim about a parameter of a population. Now, look, it's a claim about a parameter of a population. That's all we can do. We can only get point estimates. We can't do anything else except claim something about the population. Then we use the samples to help us to back up that claim, okay? Either to retain the claim or to reject the claim. Now, so it's a way of testing. There are two ways in which we can test a hypothesis. First of all, we can test it using the 95% confidence interval that we dealt with in the previous lesson. Or we can simply test it by looking to see where does it lie on the normal curve, okay? Now, the first part is quite easy. You build your confidence interval and then you simply ask yourself a question. Is the statement within that range or is it outside that range? And if it's within the range, then you retain the hypothesis. If it's outside the range, you reject the hypothesis. The Z-score, which is a little bit more tricky because it goes into p-values as well, but that basically says this. I just want to demonstrate this very quickly before we move on. Here's what it says. It says on the normal curve, because I want to have 95% confidence in what I'm going to say, in either retaining or rejecting, all right? The 1.96 and the minus 1.96, they're the magic numbers with the 95% confidence, okay? Obviously zero's in the middle. So these two are the magic numbers when it comes to 95% confidence, all right? So if you take the minus 1.95 and the 1.95, isn't it? 1.95, yeah, 1.96. If you take the 1.96 and the 1.96 there, the magic number of 95% confidence interval, well then we say that within that there is 95% of the population. Okay, now where's the other 5%? The other 5% are in two different areas, meaning that there's 2.5% of the population there and 2.5% of the population there. So either you are within the 95% or you are within the 5%, okay? And that's what we call the 5% level of significance, L-E-V-E-L, level of significance. And I did mention that before, okay? So the 95% confidence, and then you have the 5% level of significance. Both of them can be used in exactly the same way. So if it's a case that your Z-score falls within your 95% confidence interval, well then we can simply say, is the Z-score between minus 1.96 and 1.96? Or is it outside those values? If it's inside, well then you retain. And if it's outside, you reject. It'll make more sense when we do the questions on these things. Okay, so if it's within the two, minus 1.96 and 1.96, that means you retain the original hypothesis. If it's outside, you reject. So it's probably the easiest one to do, because you build your confidence level, you go back and see what was the test statistic and where does it fall within that particular range. Does it fall inside or does it fall outside? Okay, so let's move on. So get rid of that first. Okay. The null hypothesis, HO, is the statement that the value of a population parameter is equal to some claimed value. Now notice what we say. The value of a population parameter is equal to. So therefore, you see it in brackets, this is the most important thing. HO will always be equal to the claim. Okay, always be equal to the claim. And that means then that the only other hypothesis that's out there is what we call the alternative hypothesis. So your null hypothesis, HO, is always equal to the claimed value. Okay. The alternative hypothesis, H1, is a statement that is different from the value that you assumed. So in other words, to cut it down short, HO, the null hypothesis, is always equal to the value. H1, which is the alternative hypothesis, is not equal to that value. Okay. Hypothesis testing in the first place, as I talked about a moment ago. You set up your 95% confidence interval. They don't usually ask you for any other level of confidence. It's normally 95%. But if they do, remember the 1.96, the magic number, that can be replaced with something else. That's the only difference in the confidence levels, okay, is the number in front of the standard deviation. So don't worry about that. Normally always 95% as far as the exams are concerned. So when testing hypotheses about proportions, we set up a confidence interval for the population proportion at a given confidence level. Now please remember, you're setting up a confidence interval for the population proportion based on the sample proportion. Okay, remember that the population proportion is only a claim. I can't count it, I claim it. So therefore, if the population proportion is a claim, where's my evidence? My evidence is in my sample proportion. So when you're working with a population proportion claim, you use the data that is given to you by the samples that you're working with. If the HO is within the confidence interval, HO, if the null hypothesis, if your original claim is within the confidence interval, that means between minus 1.96 and plus 1.96, in that region representing 95% of the population, then we simply retain the null hypothesis. We don't say it's correct. We just say we retain it, okay? And likewise, if the HO, null hypothesis value, is outside the confidence interval, then we reject HO, but we never say that it's wrong. So if it's inside, we retain. If it's outside, we reject. They're the two words you have to remember in terms of your hypothesis. The second way to do, as we said already, is to convert to a Z-score and turn it into a test statistic. Okay, so the Z-score obtained is within the region known as the critical region. So it'll be somewhere, if it is in the critical region, then we reject the null hypothesis. Now what does that go back to? What's the critical region? Well, let's just go back here. The critical region is the region that is outside 1.96 and minus 1.96. So therefore, if 95% of the population exist between those two values, as I said already, then the remaining 5% are in these two regions here. Okay, and they are the critical zones. So both critical zones together are 5%. So don't forget, you've got two critical regions giving you 5%, which means one critical region is 2.5%. Now, this comes into what we call two-tailed testing. Okay, as soon as you're told that your statistics are normally distributed, it's a two-tailed test. What the hell does that mean, a two-tailed test? Okay, it simply means that the critical region is in both ends of your normal curve. All right, the non-critical region is the middle, and there's only one of them. but the two tails of the normal curve are both two critical regions. Together, they have a percentage value of 5%. Individually, they have a percentage value of 2.5%. So in other words, that there is 0.95. This one here is 0.025, and this one here is 0.025, meaning that as far as we're concerned for calculations, the critical region will have a value of 0.05. So even though it's a two-tailed test, both tails, there's tail number 1 and there's tail number 2, both tails equal 2.5%. And if both tails are critical regions, then the overall critical region has a size of 5%. Hope that makes sense. Okay, just think about it that way. The non-critical region, the middle, between minus 1.96 and 1.96, that's 95%. So therefore the two tails must be 5%. So watch that value of 0.05. Okay. Now, for 95% confidence, plus or minus 1.96 is the critical region, which we already told you is 0.05. Both of those be 0.05. And again, we said to you already that if the z-score has an absolute value of greater than 1.96, so that means less than minus 1.96 or greater than plus 1.96. If it's outside those, if it's in the critical region, you reject. Wherever, if the z-score has an absolute value of less than 1.96, then that means it's in the safe zone, so to speak. It's in the 95% confidence interval. So once it's in there, in that non-critical region, then you retain the null hypothesis. The significance level, last sentence there, is the probability that the test statistic will fall in the critical region, which, as we said already, is either referred to as the 95% confidence interval or a 5% level of significance. So there's the diagram that explains it all to you. There's where you have your 0. There's your first minus 1.96, then 1.96 over here. So 1.96 is there at the second standard deviation. 1.96 is here, okay? That's minus 1.96. That's plus 1.96. Now look at this value here. This value here falls inside the non-critical region. So if my value came out as 1.94, I would accept. There it is. I would accept, or fail to reject, whichever way you want to say. But I would accept the null hypothesis, or I would retain the null hypothesis. Okay. However, if the value fell out here, let's say the value came out as minus 2.47, okay, that then falls into the critical region, and because it falls into the critical region, it is rejected. So HO would be rejected. Now, the easiest way to do this is simply to do some questions, which you will do in a moment. But just lastly, to say what a p-value is. And they sometimes ask this. The p-value is the probability behind the z-score. Okay, so when you see p-values, you take the z-score that you calculated in that question, you go to your tables and you look up the probability behind that. But because it's a two-tailed test, don't forget, the probability will be in both tails. So therefore p-values, here's the steps, p-values, you turn your z-score into a probability, which we also know is a percentage. Yeah, so turn it into a percentage that uses your tables, and then you multiply the probability by 2 because it is a two-tailed test. Meaning what? Meaning that it is in both tails. Now, why are p-values used? P-values are only used if the z-score falls into the critical region. You won't talk about p-values when you're inside the critical region, for the very simple reason that if you're inside, you retain. It's only when you reject that you use the p-values. Okay? Okay, so the p-value of hypothesis test is the probability that the test statistic or a more extreme value could occur if the null hypothesis is correct. If the probability of being greater than the z-score, it is the probability of being greater than or equal to z-score, and it's found from the tables. We know that. And then because it's a two-tailed test, as I said already, you multiply the probability by 2. If the p-value is less than the level of significance. Now, if it's outside that 0.05, well then what do? Then we reject the null hypothesis. And don't forget, as we go to the two tails, yeah, we're going into 2.5% each. So therefore, if we take the probability, multiply it by 2, and it still falls under 0.05, that means it's in the critical region. So therefore we're going to reject the null hypothesis. Now, enough waffle, let's get on with the questions. Page 159, question 4. Suppose you interview 1,000 randomly selected existing voters following a presidential election. Of the 1,000 voters, 550 reported that they voted for John F. Murphy. Assuming that there were only 2 candidates in the race, is there sufficient evidence to suggest that Mr. Murphy will be the next president? And they want you to use a 5% level of significance. Now, 5% level of significance, 95% confidence interval, same thing. So what I would do in a situation like this is I'd look to see what's the data that's given to me. Well, first of all, there are 1,000 randomly selected existing voters. That's a sample. And the sample size is 1,000. Okay, what else are we told? Whoops, that's 10,000. 1,000. What else are we told? We're told that 550 out of that 1,000 voted for John F. Murphy. Well, that's a sample proportion. It's a portion of the sample. So that's p hat, which is 550 out of 1,000. Now, once you get p hat, you automatically have to write down 1 minus p hat, which is the fraction that would be added to 550 over 1,000 to give you 1. Okay, so that would be 450 over 1,000. Okay. And what does it say then? Assuming there were only 2 candidates in the race. Okay, so it's either going to happen or it's not going to happen. So there's either going to be an acceptance or a rejection, all right? Because there's only 2 candidates. So what do? The very first thing I do is I build a 95% confidence interval. Now, how do I do that? Well, you go back to what you learned in the previous lesson. What is the 95% confidence interval for a sample proportion? And the answer is, it's p hat plus or minus 1.96 times what? Times the, where are we doing? The p hat by 1 minus p hat, if you remember, all over n. And that's the square root of all of that. So that's what you've got to learn from the previous lesson. So it's p hat plus or minus 1.96 times the square root. Now, I was going to say that I was thinking of it. It's the standard deviation of the sample proportion. That's what I was trying to say, and it took a block. But that's what I'm trying to say to you, because it's always 1.96 times the standard deviation. But because it's a sample proportion, it's the standard deviation of the sample proportion, okay, which is the square root of p hat by 1 minus p hat over n. And all you've got to do then is fill them in. So you get 550 over 1,000 plus or minus 1.96 times the square root of 550 over 1,000 multiplied by 450 over 1,000 all over 1,000. Now the lovely thing is your calculator will do this for you, providing you tap it in properly. So 550 over 1,000. Now let's go to the lower value first. So minus 1.96 times the square root of fraction and fraction. So we've got 550 over 1,000. And again, make sure you press your keys slowly and make sure they all go in. Multiplied by the fraction, which is 450 over 1,000. And then that's over 1,000, which is the value of n. And the first value comes out as, in the lower regions, the lower regions is 0.5191. Now, what's the upper region? The upper end of this range, changing the minus for a plus, comes out as 0.5808. Okay, so what does that mean? That means that we accept the null hypothesis if the percentage mentioned in the question is between 51.91% and 58.08%. Now, what statistic am I testing? I'm testing this statistic, 550 out of 1,000. In other words, I'm testing p hat. Does p hat fall within those values, or does p hat fall without those values? Well, p hat is 55%, so therefore p hat fits nicely inside that range. So therefore we retain the null hypothesis to say, is there enough evidence to suggest that Mr. Murphy will be the next president? A big yes. There is enough evidence. Why? Because the test statistic the sample proportion, which in this case we're dealing with now, falls inside that 95% confidence interval, and therefore we retain the null hypothesis, which says that John F. Murphy equals president. Done. Okay. Let's go to question 7, because I want to just get taking the p-scores done, or p-values. A particular machine produces metal rods that are normally distributed with a mean length of 210 and a standard deviation of 6. The machine is serviced. Following the service, a random sample of 100 rods is taken, and the mean length of the sample is found to be 211.5 with a standard deviation of 6. Is there evidence at the 5% level of significance of a change in the mean length of the bars produced? And then it says give a p-value for this hypothesis test and interpret this p-value. We'll come on to that in a moment. Okay, let's go back to the beginning. What are we dealing with? A particular machine produces metal rods that are normally distributed. Now, what's normally distributed? The population of metal rods. We're talking about all the metal rods that it produces. So the very first set of figures are parameters. All right. So a mean length of 210, but that's a population mean. So that's mu of 210, and a standard deviation of 6. Okay. The machine is serviced. Following the service, a random sample of 100 rods, so n equals 100, is taken, and the mean length of the sample, x bar, is found to be 211.5, with a standard deviation also of 6. Is there evidence at the 5% level of significance of a change in the mean length? Now, first of all, what data have we just been given? We've been given 2 population parameters, namely the mean of the population and the standard deviation of the population, but we've also been given some statistics about the samples. N equals 100, x bar equals 211.5, and the standard deviation sample is also 6. So in this case here, you have to try and figure out, where am I going to use these? And if you remember, you're going to use them in order to calculate the z-score of 211.5. Okay, is there enough evidence? See that? Is there enough evidence at the 5% level of significance of a change in the mean length? Now, therefore, I need a null hypothesis. I need a HO and I need a H1. Remember what I told you about HO? HO is always equal to the sample, or sorry, to the mean of the population. So in this case, it says the mean of the sample is found to be 211.5. Is there enough evidence to suggest a change? Now we're going to say, okay, HO, my hypothesis is no change, it's still equal to 210. My alternative hypothesis will not be equal to 210. Okay, so therefore your null hypothesis refers to the population. Just keep that in mind. The null hypothesis, it's a hypothesis about the population, which we're going to try and test using the sample statistics. I hope that makes sense to you. So therefore, when you're dealing with HO and H1, they are values that come from the population, and the only value you have of the population is a length of 210. So therefore, my hypothesis is this. My null hypothesis says the following, that the length will be the same. The length is 210. Whereas my alternative hypothesis will say it's not equal to 210. Now, there's another way to say that, okay? And I don't want to confuse you, but I just want to give you the option of being able to say it this way. The null hypothesis is equal to the original length, which also means that there is no change. See? There's no change from the original population mean. The alternative hypothesis is that there is a change. That's what they mean. Okay, and I hope that makes sense to you. I prefer to stick with the first version. Null hypothesis equals to the parameter of the population. The alternative hypothesis is not equal to the parameter of the population. The parameter in this case here is the length of those particular metal rods. So what have I got to do? Work with z-scores. We know that for a sample, or what we call here in this case a sample proportion, we know how to get our z-scores. It's x bar, the sample proportion, minus the population proportion, over the standard deviation divided by the root of number of people in your sample. Now that's a formula you just have to learn off. It is in your tables. Not too sure what page. Can't see me tables around the place. Not too sure what page it's on, but it's there somewhere. So let's fill it in. And usually, by the way, when you see the statistics that you gather, the statistics will normally point out what formula to use. Okay? What's the only formula with mu and x bar and n and sigma? Well, it's the standard deviation of a population or a sample proportion. That's it. So let's fill them in. X bar 211.5 minus mu 210 over sigma 6 divided by root n root 100. And again, don't even worry your heads about doing it. Shove it all onto the calculator. That's 1.5 on the top because 211.5 minus 210, 1.5. So just put the 1.5 on the top. And then the fraction on the bottom is 6 over 10. Or 6 over root 100, whatever way you want to put it yourself. And that comes out as 2.5. So now we get z equals 2.5. Now, remember what we do with z-scores? Look to see where they are. Where are they? We look to see, where's 2.5? Now, that's 0, 1.96 minus 1.96. Where's 2.5? 2.5 is out here somewhere. There's 2.5. Where is it? It's in the critical region. What does that mean? That means that we reject HO. So you reject the null hypothesis in favor of the alternate hypothesis. So what's the results of what's the conclusions of my findings of my statistical exercise? There is a change. Okay, so go back. Is there evidence at the 5% level of significance of a change? Answer, yes. Why? Because we rejected the null hypothesis that there was no change. We rejected the null hypothesis that the population mean of 210 centimeters was maintained. Clearly here, that's not the case. The z-score of the sample mean, when it becomes 2.5, so when the sample mean is turned into a z-score, it becomes 2.5, which is in the critical region. The critical region, don't forget, is the one that's below minus 1.96 and the region above 1.96. So obviously 2.5 falls in there. So since, and all I've got to say here is, since 2.5 is greater than 1.96, we reject HO. That's all you've got to say. That's it. Now, is there evidence of a change? Yes, there is. Okay, give a p-value for this hypothesis test. Now, I have to remember the z-score is 2.5, okay? I'm going to have to make a bit of space here. So let me just maybe just take these off here. Let me just take all this here away so I can get a bit of space for the p-value. Okay. Now, give a p-value. Here's what I want to do. I want to find out, remember what a p-value is. It's the probability that the z-score or greater, remember I said that? It's the z-score or more extreme. So the probability that z is greater than or equal to 2.5. That's what I want to find. However, the probability of being greater than or equal to 2.5 is there. But it's a two-tailed test. So therefore, it's also going to be here. So what I have to do with this is, because that only represents one tail, is I would have to multiply the whole thing by 2, because it's a two-tailed test. Okay. Now, what's p of z greater than 2.5? Go to your tables. They're hiding behind my iPad. Okay, so go to your tables, go to your z-scores, work out what it is. Now, first of all, if we want the area in front of 2.5, I can't get it. So that means it's 2 times 1 minus the probability of z, it's 2 times 1 minus the probability of z being less than 2.5. Okay, so in other words, it's going to be this, to get this area here, it's 1 minus everything that's behind it. So go to your tables. 2.51, what does that come out as? Well, 2.51 comes out as 0.9940. 1 minus 0.9940 is equal to 3 over 500, which is 0.006 multiplied by 2 comes out as 0.012. Now, for the 5% level of significance, we're looking at this. How does that compare to 0.05? It is less than, yeah? So you'd say this one here is less than 0.05. And if it's less than 0.05, it's the same conclusion. Because it's less than 0.05, that means that we're still in the critical region and we're going to reject the null hypothesis in favor of the alternate hypothesis. So basically, the p-score just backs up what you found in terms of your 5% level of significance. Yeah, that's all it does. So the p-value It just backs up what you did in terms of your z-score. Your z-score helped you to see where it was in a normal curve. Was it in the critical region? Was it outside the critical region? Did you accept and retain the null hypothesis, or did you reject the null hypothesis? The p-value does exactly the same thing. So just remember the p-value. The p-value is the probability of greater than or equal to the z-score you get. But because it's a two-tailed normal distribution, you always multiply the p-value by 2. Okay, and then when you do that, check and see what does your probability come out of in terms of how does it compare to 0.05. If it's less than 0.05, that's the 5% significance level, we reject the null hypothesis. If it comes out as greater than 0.05, well then we simply retain the null hypothesis. But don't expect to get a different answer with your p-value as you're going to get with your z-score. They both back each other up because they both represent the same sample statistics and population parameters. Okay, I'm going to leave you with these final questions. This is it now. Page 159, page 160, question 2 and 3, 5, 6, 8 and 9. We will come back with a live class just to discuss what we've been doing over the last 3 or 4 classes, to put it all together. And then I do want to go into some exam questions on the papers based on probability and statistics together. And I'm going to take quite a while on those questions. I want you to see how they're all worked together. But that is the end of your statistics. That is that section finished, along with your probability. Marry the two together if you can. And they will be married together in most cases in some of the larger questions or longer questions that are towards the end of paper 2.